All right, that's fair dice. So this is the distribution we played with a couple weeks ago, and it's the distribution you play with if you're playing craps, if you're playing Monopoly, if you're playing any two dice based game. That's the sum of the pips. On average, you get a 7 plus or minus a 2.4, plus or minus 2.4. No problem. Now we start getting into the fun dice. Here's the blue distribution I got. Who had blue? A couple of you guys have blue, right? Yeah, good. See if this matches what you guys got as far as the shit. Now, you might not have done a distribution if you were feeling saucy. So here's a distribution, but you can pull the frequencies off pretty easily. 1, 1, 2, 2, 3, and so forth and so on. I got an average of about 8.17-ish, plus or minus about a 2.65.
Exactly.
So, thank you. Excellent. I didn't have to write that. God. So I called it skewed left, only because it's leaning this way, which means the average is a little bit left of where like the biggest humps are, if you will, a little bit, not much. It's slightly skewed. A lot of people would call that bell-shaped enough. It's just this kind of gave me pause. The 11 spike was like, If it was a little bit lower, I'd feel a little happier calling it a bell. Because of that spike, it looks like it's leaning a little bit this way. So I called it skewed. You can call it whatever you want. The key is, it's got an average, which is that, and it's got a standard deviation, which is that. And we can call them mu and sigma because I told you those were your populations. This is your population, which is a bit fictitious. We'll get to that momentarily. Okay, good. There's blue. Here is what yellow looks like, at least what I think yellow looks like. We kill the lights. Yellow is kind of light. Is that in agreement with you guys? Yeah. Average of 4.5? Okay. Plus or minus 2.22. Yeah, the lion's share of your stuff is down here. The lion's share of your stuff is down here, and then it's got this great little tail. That's a highly skewed distribution, highly skewed. And you can see the average is over here, where most of it's over here. So your average is heading towards that 11 that's over here, tucked up in the corner. Good. So I'm not saying we should trust the average. I'm just saying that's what the average is of that population. I mean, you can talk about whether you should report it as typical or not. And we've done that for weeks now. Let's just worry about we can calculate that. There's green. I call this symmetric wide. Some of my students call it the flipping you the bird distribution. I like that one too. Kind of fun. This is the only one where both dice were exactly the same. I was trying to make a U-shaped distribution. I wanted to get one that went like this, like a Weibel. It's called a Weibel distribution. Tell me why I couldn't. I settled on this. I'm like, this is kind of cool. Why can't I get a U-shaped one for a pair of dice? Why can't I get this without that spike in the middle there?
Because those middle numbers happen more often.
How come? Suppose I wanted a spike over here, yes?
They're more common.
Mon, go.
Well, isn't it because you can, with this, if you're getting a lot of the smaller and the bigger, you can make the center one.
That's the problem. If I get a spike over here at 12, that must mean I got a bunch of 6s and 6s on the 2 dice. And if I'm getting a spike over here at 2, that means I got a bunch of 1s and 1s. Well, if I got a bunch of 6s and 1s, what else do I have a bunch of? 7s, by definition. I settled on this one because it's about as close as I could get. So I lived with it. It's fun. Flipping the bird. This is a fun one. This was a fun one. Little bimodal orange. Some of you guys had orange dice. Just match what you guys got. We got an average of 7, just like the last one. Just like the last one. Last one's got an average of 7 and a standard deviation of almost 3. This one's got an average of 7, but a slightly tighter standard deviation because it's closer in towards the middle. But again, the average of 7. There's 7. There's the 2 modes. So I like this one because, again, perfect example of why you might not want to report the average when it looks kind of like this. Good example of that. And is this an agreement with you guys with the orange? We good? Thumbs up? How many orange? There should be 2 sets of orange dice. You guys and who else had orange? Somebody else had. David, you guys have orange?
Yeah, we have.
Is this an agreement with what you guys are getting?
Yeah,
excellent.
We got standard deviation of 2.1718.
Good enough, good enough. That could be a rounding error on my part. And here's red. The only one that kind of looks like a bell. You guys had red and somebody else had red. You guys had red there. The only one, this was full of large numbers, which means your average is slightly larger than the other ones, 9.2 versus 7 and things like that. Very, very small standard deviation by comparison because everything's crunched in really closely. Everything's crunched in really closely. I want to share with you how I did this. I gotta go back to here. What I did, because I'm me, I wanted to make fun dice for you guys to play with. So what I did was I set up random integers between 1 and 6 for the 2 dice on these 2 columns, and I put their sums in here, and then I just kept pressing F9 and kept re-rolling them until I saw something fun. And then I took a screenshot and then built those dice. So, it's kind of fun. So you get, you basically just keep reshuffling until you find, oh, that's kind of interesting. Anyway, fun with Excel. Again, fun with Excel. You guys happen to, the 5 that I got with the 5. I found one, oh, you can't even see that whole damn chart. I'm sorry. Stupid computer. There you go. Not that it really matters. You can kind of see what's going on. So, that's the fiction. The fiction is I just handed you a pair of dice and said, calculate mu and calculate sigma, which is calculate the population mean and the population standard deviation, which is a little bit fictitious. For certain things, it's fine. For probability distributions, it's pretty much okay because you've assumed that you've sampled so much, you've got the actual population probabilities, and the margin of error has shrunken down so much it can pretty much be ignored. More on that today, too. But in reality, that's kind of false. You can't get mu or little sigma. If you can't get mu, what can you get instead? What's the sample version of mu? We used to talk about it quite a bit. Do you remember? You might have forgotten. That's okay, too. X bar. Good. It's been a while, right? We keep talking about mu. We've been talking about probabilities and mu for so long. And if you can't get little sigma, which is the population standard deviation, who's the sample version of that? You saw it right above sigma on your TI.
It's SX.
Little s, right? SX on your TI, little s. So let's take our 5, and that's where the quiz will come in. We're going to sample from this population. We're going to sample from this population. We're going to play Gallup, we're going to play Quinnipiac, we're going to play CNN. We're going to pretend this is our population and we're sampling from it, and we're going to see how close we can actually get to the true value of the average. Because we are interested in the average, we just can't get it directly. So we're going to try to get it indirectly, and we're going to see how good we can be. Make sense? Week 10, baby! You guys, I'll take you guys up yet. I got another hour. All right, take 5. Recharge. Recharge. Get